Hey everyone, this is chapter 6, Ionic and Molecular Compounds. So let's get started. So this is really getting into chemistry and how it works and how atoms are bonded, and it's going to lead us into how reactions happen. And this is really relevant for pharmaceutical industries and that part of healthcare, and can kind of lead us into learning about what drugs can do and different medicines and things. So in this section 1, it's about ions, the transfer of electrons. So we're going to learn about what ions are and how they behave. When an atom loses or gains electrons, it becomes an ion. And then when it shares electrons, it becomes a molecule. Those are covalent bonds. So lose and gain is ionic bonds. And they're all going to do this in order to get 8 outer electrons, unless it's hydrogen, it'll gain 1 electron or lose 1 electron, and to get 2 or none. But otherwise, they're all going to get to that 8 valence electrons. And to do that, they're either going to form an ionic or a covalent bond. So these are the 2 different types of bonds. Ionic bonds are when you have a metal and a nonmetal, and you are gaining or losing electrons. So that's a good thing to remember for that. And these are only the valence electrons. So remember, that's only the outer electrons. Covalent bonds are between 2 nonmetals, or more than 2, and they are also going to get a noble gas arrangement. So they're going to get a full octet, full outer shell with their valence electrons, but these are going to share electrons. So ionic bond is gain and lose, and covalent bond is share. Here is an example. We have this atom here. It has 1 valence electron, and so it's going to give up that electron to this guy that has 7. So you can see here it gave it, this one took it, so give and take, and they're going to stick together. This one's going to be positively charged, this M, because it lost an electron, and then the NM, the nonmetal, is going to be negatively charged because it gained an electron. M and NM don't actually exist, those aren't elements, so they're just using that for metal and nonmetal. So that is an ionic bond. A covalent bond, you have 2 nonmetals. These 2 happen to have 7 outer electrons, so they're going to actually share these 2 lone electrons here, and that means they each have 8 electrons. So this one over here has 8, and then this one right here also has 8 electrons that it's sharing. Okay, so positive ions are always metals, and they always lose electrons. So metals lose electrons. The ones that do this are in group 1, 2, and 3. So you have the alkaline metals and the alkaline earth metals, and then group 13 or 3A. They tend to have low ionization energies, and they can easily lose 1 or 2 or 3 electrons from their outer shell, and that's going to give them the positive charge. And they're going to end up with a complete outer shell by losing those few that are on the outside. Underneath, they're going to have an outer shell. These guys are called cations. They're positively charged ions, and they're called cations. So here are some examples. Sodium is in group 1A, and it has 11 electrons and 11 protons. So it'll have 2 on its first shell, 8 on its second shell, for a total of 10, and then that last one, number 11, will be on its valence shell out here. And so it's going to get rid of that 1 electron. When it does, then it only has 10 electrons, but it'll still have 11 protons and 11 electrons. So it actually has 1 more positive charge than negative, and that's what, so you can see that here. That's what gives it the positive charge. So now it goes from neutral sodium to Na+, and this form is more stable. Notice that it got smaller too because it lost that outer shell. So now it has just this inner shell filled with 8 electrons. Magnesium is another example. This is in group 2A, so it's an alkaline earth metal. It's going to have 2 electrons on the outer shell. So when it loses those 2, loses that whole shell, and then here you have a full shell of 8 and 2 on the inner shell, 8 electrons. So now you still have 12 protons and you only have 10 electrons, that means magnesium has a +2 charge. And that's its oxidation number. Negative ions are on the other side of the periodic table, so these tend to be in groups 15, 16, and 17. These are usually nonmetals, and they tend to gain at least one electron, one or more electrons. They have high ionization energies, which means they gain electrons easily, and it's hard for them to lose them. They want to gain enough to have a complete outer shell, which is usually 8, and these negative ions are called anions. So let's look at what this looks like. Chlorine is a pretty common one to use as an example. It's in group 17. It's a halogen. So it has 17 protons, 17 electrons, 7 on its outer shell. You can see that there. And it really wants to gain that 8th electron. So it's going to gain one. When it does that, it actually becomes bigger and fluffier because the nucleus can't hang on to that shell as easily as it did when there were 17 electrons. So now it has 18 electrons and it has a 1- charge. Here are some common ones that we'll see a lot. And the charges here in the corners, these are called their oxidation numbers. So if I use the word oxidation number, that's the number that or the charge that they get once they've become an ion. So these in groups 1, 2, and 3 become positive cations. They're metals. And then the ones in 5, 6, and 7 become anions, negatively charged atoms, and they are nonmetals. And then this is how you name them. So these positive cations just get named with the regular name. And then the anions have the regular name, but then you add I to the end. Here are some other examples, just ordering them in groups 1, 2, and 3 with metals, and then nonmetals, groups 5, 6, and 7. And then your noble gases, remember they have 8 outer electrons, so they're not going to usually gain or lose any electrons. But what this also shows us is that these guys, when they lose their outer electrons, they're going to become like neon. And then these, when they gain 3, 2, or 1 electrons, they're going to be like neon. So that's what that's also showing us. Lithium will lose 1 electron and be like helium. One shell. Here are some examples of why some of these ions are important in health. So you probably have heard of sodium, I hope. That is a cation, the stuff that's in your body that runs around and it serves as an electrolyte is a positive ion. So is potassium, calcium, magnesium. And these are all the functions that they're for right here and where you can find them in food. And sometimes we have to take them as supplements too. All right, let's see if we can write the formula and symbol of an ion with 16 protons and 18 electrons. So go ahead and pause to do that. So that element would be sulfur. The symbol is S. And if it has 18 electrons, it's going to have an oxidation number or charge of 2-. So that's your answer. That's a sulfide ion. That's its name, is sulfide. Consider the elements calcium and chlorine. Identify them as a metal or nonmetal. State how many valence electrons. State whether the electron that must be gained or lost for each to acquire an octet. And then write the symbol with its charge and the name. So pause and do those things. Here's your answer. The name is, calcium is a metal and chlorine is a nonmetal. Calcium has 2 valence electrons and chlorine has 7. And that means that calcium is going to lose 2 and chlorine will gain 1. These are their charges and names. So this is calcium 2+, calcium ion, and chloride is a Cl-. All right, let's move on to the next section. So in this section, we're going to be looking at ionic compounds and how they actually bond together. So we're going to be bonding positive and negative charges and look at how they actually form ions like this salt crystal right here. Ionic compounds are composed of metals and nonmetals, so they have positive and negative ions. And when these bond together, when the positive and negatives attract, they form an ionic bond. These have really high melting points. For example, it's really, really hard to melt salt, but they are solids at room temperature, and most of the time they dissolve in water, but not always. So salt is probably the most common that we give as an example. We've talked about it before in these videos. Salt is sodium chloride, and it's known as table salt. If you look at this magnification, it's these perfect little square crystals that you actually see when you're looking at table salt. And these are made of sodium metal, which looks like this, and chlorine gas, which looks like that. But when you chemically bond them together ionically, they're going to form a white crystal, and that's because the sodium and chlorine atoms are bonded like little bricks. Every other one is a sodium or chlorine, and they make this perfect crystal shape. So we use chemical formulas to show what the ratios are and what atoms are in a compound, and they should equal out to neutral. So if you look at all the different charges in a formula, it should become equal. So here's an example of that. You have sodium is going to have a +1 charge, and then chlorine is going to have a -1 charge. And so those all equal out. The positive and the negative, you have one of each, and it cancels out. Now, if you have uneven charges, then you still have to cancel them. So what's going on here is the magnesium is going to lose 2 electrons, but each chlorine can only take 1 electron, right? So you need 2 chlorines to satisfy that 1 magnesium. This is what it's going to bond like. And your formula is going to be MgCl2. And we use a subscript here. You put it down below at the bottom to show that that's the formula, and that's how many chlorine atoms you have. Here's another example. In this one, sodium each has 1 to give, and sulfur has 6 electrons, so it can take 1 electron from each sodium. So here's your charges, Na+, Na+, and S2-, and your overall formula is Na2S. Let's see if we can do this with barium 2+ and Cl-. Pause the video and try to write the formula for this. So these are your symbols, and barium has a 2+ charge, chlorine has a 1- charge, so this is what your formula would be. And what I teach my students is that you basically take this number, the oxidation number, lasso it, and bring it over here. And then you take this number, 1-, lasso it and bring it over here, but you also drop the charges. So since I'm canceling charges, I don't care about the positive and negative, so it's just going to be Bl. You could put a 1 here if you wanted to, and then Cl2. So that's how you do that. All right, so let's see if you could answer these 3 questions, matching the formula to what ions are being bonded. So pause the video and try that out. And there you are. There's your answer. And we check to make sure the charges zero out perfectly. Okay, next section is writing, naming and writing formulas. So we're going to learn more about the formulas and how to name them. And it's kind of like learning a new language, but it's pretty easy. So when we name ionic compounds, first we say the name of the metal. That's the first name. And then the last name is the name of the non-metal, but you add "ide" to the end. You drop the last part and add "ide," and then you put them together, and there's a space in between. So here's some examples. Ki is potassium and iodide, so the name is potassium iodide. And here's magnesium bromide, so there's your name, and then aluminum oxide, there's your name. So here are your steps. First, you identify which one is the cation and which one is the anion. We always write the metal first in a formula of an ionic compound, and then the non-metal. So make sure you have metal, then non-metal, cation and anion. Then you know you have it in the right order to name it. And then we name the cation, which is just potassium. Then we name the anion, which is oxygen, but you drop the ending, so it's oxide, and then you put them together, potassium oxide. Pretty easy. See if you can name these 3 ions, these 3 compounds. So there's our first step. We're identifying the cation and anion for each. And you could see that we kind of split them apart, and then we named the cation. So there they are. And then we named the anion, adding I to the end. So there's your final name, putting them together, first and last name. Okay, so see if you can write these formulas and the names for each of these. And there they are. Follow those 3 steps and you got them. The one that's tricky is this one right here. So you might have named it Al3N3. When they have the same charge and their ions, then you drop those numbers because you need just equal ratios of each, but that's only with ions. I think the rest of them are pretty straightforward. But yeah, if they're equal numbers there, you drop them. Okay, now we have some metals that are a little bit different. So the last ones were for type 1 metals, and these are considered type 2 metals. These are a little bit different. These are metals with a variable charge. These are in the transition metal part of the periodic table, which is that middle chunk. And these metals have more than one option for their oxidation number. So they can have more than one charge. Here's an example. Copper can have 2 different numbers. It can have a 2+ or 1+. It depends on the type of copper it is. Iron is also a type 2 because it has 2 different options. Lead has 2, chromium has 2. There's a handful that have more than 2 also. So when we're naming these that have more than one option for their oxidation number, we actually use Roman numerals. So if you're naming it, instead of just saying copper for the metal, you're going to say copper 2 or copper 1, and you have to put something. You can't leave this blank. You have to put some number. It's either going to be this one or that one, this one or that one. Some of them only have 1, and these are the ones that are in the transition metal chunk of the periodic table, but they only have 1 option, so you don't have to use Roman numerals for those. So here are the ones that have the variable charge. We have bismuth, chromium, cobalt, copper, gold, iron, lead, manganese, mercury, nickel, and tin. The one that's weird is mercury. That one's kind of a tricky one, so you can see that here. It's kind of a strange version of the mercury one. So those are some different ones that are in your book. And here's how we name these. So manganese is one of them. If this is your formula, that means the oxidation number of the manganese is 2+. So your name is going to be manganese 2 fluoride, and you're specifying that you have the 2+ form of manganese. Here are the ions on the periodic table, the main ones that we use. So these are all the regular ones that we've used along with this guy. They all just have 1 charge. So all these have a +1 charge, all these have a 2+, and these have a 3+. Some of the metals, though, have multiple charges. So you can see these transition metals here that were on that list on the last slide. These have 2 charges. These are the ones we have to use Roman numerals for. And then these over here, these will always only have 1 charge. These are the anions, these are nonmetals, and you don't have to worry about them in your naming. So here is how you name these, the ones that have a variable charge. Let's say we have FeCl2. We notice that this is a transition element and we don't know what charge it is, so we have to specify. When you unfold this and see that that 2 came from the iron, then it does have a 2+ charge and the chlorine has a 1- charge. So then from that you find that you're looking at iron 2 and you name it iron 2 chloride because it had the 2+ charge. Let's see if you can name this one, SnO2. So here you find, this one's tricky. When you unfold it, for it to have an overall charge of 0, oxygen always has a 2- charge. So here's your 2-. For these to have equal charges then, tin would have to have a 4+ charge. So this one is actually tin 4 oxide because the tin has to have a 4+ charge. And so those charges kind of reduce down when you switch them around. Here are some examples of some different ones and their names. So you have those parts, but those are only for the metals that have a variable charge, and you have to specify which one. Okay, let's see how we do on this one. So here's our name, iron 3 chloride, and we have to make the formula. So if we have iron 3 chloride, that means that we're using Fe3+, and then chloride is always 1-. And you switch the charges, so your final formula is FeCl3. Let's see if you can write the formulas for these three. So here are your three. You're identifying the cations of the three and the anions, and then you're going to switch the charges. So here we go. So you switch this one and you get nickel 2 sulfide. This one's going to be zinc chloride. You don't have to specify the 2+ charge because zinc does not have a variable charge. There's only one kind of zinc. And then iron 3 oxide, you do have to specify because there can be two kinds of iron. So here are your names and your formulas. Now we're going to look at some polyatomic ions. These are some weird ions that can form out of more than 2 atoms, so 3 or more atoms. And one example is the sodium chlorite, which is in your contact lens solution if you happen to wear contact lenses, and it's also used for other things. So we're going to look at what polyatomic ions are and how we can use them in naming. Polyatomic ions are overall an ion, so they overall have a charge, but they are made of covalent atoms, covalently bonded atoms. They usually have nonmetals in them, so they usually have phosphorus, sulfur, carbon, or nitrogen, and also oxygen. And these are usually negatively charged. Most, like 99% of the time, they have a negative charge. They are anions. They have a negative charge of 1, 2, or 3. But there's one exception. There might be more, but there's one common exception, and that's ammonium. So ammonium is a positively charged polyatomic ion, but most of them are negative. So here are some examples here. This guy right here, this sulfate, this is a polyatomic ion. It's made of sulfur and 4 oxygens, and overall it has a 2- charge, so it is an ion, but these are covalently bonded. Here is ammonium. This is positively charged, it's NH4, so it is made of covalent bonds, but overall it's an ion. And then nitrate is also a polyatomic ion made of NO3. Overall it has a -1 charge. And so these are some examples of where you see them in everyday life. This is a cast and this is fertilizer. Here is a list, a handy list of some polyatomic ions and their names. These are kind of hard to memorize. So you have this handy list also. Keep that bookmarked so you can find it. I have to look some of these up if I don't use them a lot and don't remember the formulas sometimes. But there are some patterns that we can look at here in the naming. Notice that you have up here, you have nitrate and nitrite. They have nitrate bolded. That's the most common one that you're going to see. Nitrate is NO3-, and then nitrite has 1 fewer oxygens. So we name that nitrite. And then here we have ClO3- is chlorate. Then the one right under it that also has 1 fewer oxygen, kind of like here, is named chlorite. So we can see that pattern. However, I'm just going to hop down to the sulfate and then I'll come back up. Just because it has 3 oxygens doesn't mean it has the ate suffix. So here you see SO4 2- is also called sulfate. So we can't, same here with phosphate, PO4 3- is phosphate. So we can't say that if it has 3 oxygens, it has an 8. So these are a little tricky to memorize, but you'll pick up some patterns. Notice here, I'll come back up to chlorate. If it has another oxygen, we call it perchlorate, so that's ClO4-. And then if it has 1 fewer, going from 2 to 1 oxygen, we call it hypochlorite. And there are other ones that have the same pattern that we see here. And we can see some of these other ones. Cyanide you probably heard of, and acetate. Here's sulfite. It has one fewer oxygen, so sulfate, sulfite. And then along with hydrogen, it's hydrogen sulfate, sulfite. And here's phosphate and phosphite, and some other ones. So those are some common polyatomic ions. Remember, those are covalently bonded, but they are ions. They have a negative charge except for ammonia. Hydroxide here, also don't miss that one. That's a common one. Okay, so here are some common ones. These are the ones that end in ate. These are the ones that end in ite. So that's what I mentioned in the last thing, one less oxygen. And then here are some weird ones, cyanide and hydroxide. Here are some that have hydrogens added to them, so they have different names. And these are ones that have have different numbers of oxygens. Also notice, like all of these just have variable numbers of oxygen, but they all have a 1- charge. I forgot to mention that, so that's important too. All right, so here's how you write formulas. This is where things get a little tricky, so pay good attention to this part. If you're bonding, say, magnesium with a nitrate ion, magnesium has a 2+ charge, nitrate has a 1-. So you're going to do the lasso and bring it over, lasso and bring it over. In order to satisfy the 2+ charge of magnesium, you're going to have 2 of these nitrate ions because they each only have a 1- charge, right? So this is going to be your overall formula for magnesium nitrate. Here's another example we can try, aluminum and hydrogen carbonate. Those are the names for those. And you'll have a 3+ charge on your aluminum and a 1- on your hydrogen carbonate. So the aluminum's charge will come over here. The hydrogen carbonate charge will come over here. Let's see if you can write the formula for sodium phosphate. So pause the video, try this one out. So here are your cation and your polyatomic anion. And that's what it looks like when you have the formula. So the 3- charge from the phosphate comes over to the sodium. Okay, here are some other examples of common ones. This is how to name them. So this one is sodium sulfate. You just name it sodium sulfate. This one is using iron, and iron is a transition metal that has a variable charge. It's a type 2. So you need to figure out the charge of the iron. Since none of these have any subscripts, then the iron has to be a 3+ because the phosphate ion is a 3-. So it's iron 3-phosphate. And then this is aluminum carbonate. Aluminum has a 3+ charge always. Carbonate has a 2- charge always. So you just switch the charges, aluminum carbonate. Here are some common ones, and these are their uses. So these are, you see them everywhere. They're really important for our lives. And these are their names and their formulas. Okay, see if you can circle the correct or choose the correct formula for each of these. And there are your answers. And this is a flow chart on how to name them. So you have regular ionic ones, and you have the metal and the nonmetal. And then if you have more than one positive ion, you use or more than one types of positive ions, you use the Roman numerals. And then this is a monatomic ion with just like Cl-, and then this is your polyatomic. This is also information on how to name molecular compounds, which is when you have 2 nonmetals. So let's see if you can name these 2 correctly. And there you are, calcium nitrate, iron 3-phosphate. And what about naming these 3 polyatomic ions? So there's your names, magnesium sulfite, magnesium sulfate, and lead 2-phosphite. Okay, what about these? See if you can name these. And there you have iron 3-sulfate, barium phosphite, and nickel 2-carbonate. Carbonate is also a thing. Okay, next, this section is 6.5, molecular compounds. So these are the covalently bonded ones that are sharing electrons. So we're shifting to bonding nonmetals and sharing electrons. Okay, so molecular compounds are when you have two or more nonmetals, covalent bond, sharing electrons, and you're only sharing the valence electrons, but you are sharing these to get a complete outer shell. So you need that octet, 8 electrons on the outer shell. These are named a little bit differently, so we kind of have to shift gears into this naming. We use prefixes to name these, whereas with ionic compounds, we don't use prefixes. So these are your prefixes that you'll use, and this is indicating how many of each atom you have. And then the second nonmetal, you add "ide" at the end. So if you have two, it's mono, one is mono, two is di, three is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. And it does go higher than that, but we'll just start with those 10. So here are some examples. I'm sure you've seen these before. This should ring a bell, but remember we're only doing this with molecular compounds and not ionic compounds. So the first one here is carbon dioxide, and you're indicating the carbon and that there's 2 oxygens. And then this is carbon monoxide. Here's another one, nitrogen monoxide. If you're ending with, or if you're starting with an O, you don't put 2 O's there. You just put 1 O. So you wouldn't put monoxide. Here are some common ones that you might have heard of. So this one has 2 nitrogens, so it would be dinitrogen oxide. If there's only one of the first one, you don't put mononitrogen. You just leave it saying the name. And this is what they're used in. Okay, so here's step-by-step how to name. You look at what the first nonmetal is, and it is nitrogen. Then you look at the second nonmetal, and this one is chlorine, but you change it to chloride, and then you look at how many atoms you have of each. Nitrogen only has 1, so you don't put a prefix, and then chlorine there are 3, so you say trichloride. Let's see if you can name this one. And here are the steps. So the first one is named boron, that's the first name. The second one is oxygen, so you change it to oxide, and then you look at how many you have and add your prefixes. So in the first one you have 2, and the second one you have 3, so it's diboron trioxide. Okay, so when we are writing the formulas, we can go from formula to name or name to formula. To write the formula from the name, you just use the symbol and then use the prefixes to tell how many atoms you have. So see if you can do this one, diphosphorus pentoxide. And here is your formula. We know we have phosphorus and oxygen, and then we use the prefixes to tell us how many. So that would be P2O5. We definitely need to be able to tell if the compound is ionic or covalent, because that affects how we name it and how we figure out the formula, both of those. So when we look at ionic compounds, we're seeing that the first one is always a metal. So you look at your periodic table, you look at the colors, the ones that are on the left side of the staircase, which is most of the periodic table, those are metals. And if it's metal, it's ionic. So we name it according to that. So this one would be potassium oxide. It would not be dipotassium oxide because it's ionic. We don't use prefixes if it's ionic. And then if it's covalent, we look for that first one being a nonmetal. If it's covalent, we do use prefixes. So this is dinitrogen oxide. Okay, so here's your flow chart. If it's ionic, you name it using these rules. If it's molecular, you name it using these rules, using prefixes. So ionic does not use prefixes, molecular, covalent does. Okay, see if you can select the correct name for these. Remember, first you check to see if they're both nonmetals. If they are, you use prefixes. If they're not, you don't use prefixes. Okay, so hopefully you got those correct. And then see if you can name each of these. Oh, no, sorry. First, identify it as ionic or covalent and then name it. So these are mixed up between ionic and covalent. And you might see some that are type 2 where you have to put the Roman numerals if there's more than one oxidation number. Okay, so there they are. All right, now we're going to move into Lewis structures. This is for covalently bonded molecules. These can be regular molecules or polyatomic ions. Remember, polyatomic ions are covalently bonded, but they become ions because they have a plus or minus charge. So here are a few examples. We use Lewis structures to draw them to see what they look like, so we can look at how they bond with other things. Methane is the simplest carbon molecule. Its formula is CH4, so that's methane there. This is water over here, and then this is ammonia. So those are what some different Lewis structures look like. The simplest possible molecule that is covalently bonded together is H2. So H only has one valence electron, and when it bonds with another H, they're each going to share that one electron, so they'll have 2 electrons total. And this is used as fuel and stuff like that. So that's hydrogen is going to have a noble gas arrangement of helium when it's done bonding. Here's what it looks like when it's separate, and then when it's together, you'll see where the electrons are bonding, and it's going to be more stable and be at less energy when it's bonded as H2. So this is not a stable way for hydrogen to be. It's going to be most stable when it's bonded together. This is how we draw Lewis structures. So in this one, we are showing that we have bonding pairs in this ammonium. So this N is bonding to the H, and they're sharing a pair of electrons. Same with this, they're sharing a pair and they're sharing a pair. And then here we have lone electrons. All together, this nitrogen here has 8 electrons because you have the 2 lone pairs, and then you have 2 electrons here, you have 2 here, and you have 2 here. So altogether, that nitrogen has 8 electrons. This hydrogen here has 2 electrons. That's how many it wants. It's just sharing them. They're holding hands. And then same with these other 2. So this is a really happy, stable molecule. And this is how it would form if it was NH3. Here's another example of a Lewis structure. This is F2, a fluorine molecule. Each of these fluorines have 7 valence electrons, and when they bond, they're going to share this electron and this electron together. So here they are sharing. This fluorine now has 8 electrons, and this fluorine now has 8 electrons. So they're both happy. This is what the bond looks like. It's covalent, they're sharing. And then you have, each one has 3 lone pairs of electrons. So you can see 3 lone pairs there. This one is an F2. And they all have stable octets. These are the ones that are always going to bond with each other, like we just saw with H2. We looked at H2, we looked at F2, and these are called diatomic molecules. So these are always going to bond in 2s together. That's how they're more stable. They're not stable if they're separate, and it kind of forms this like upside down L shape and then H2. So you definitely need to know which ones are diatomic, which ones are always together. These are some other examples of how many electrons they're going to share. So hydrogen is going to share 1 electron. It's going to form 1 bond. Boron is a weird one. It's not going to form an octet. It's only going to form 3 bonds. And then this is how many bonds these other atoms are going to form. That's pretty predictable. There shouldn't be any exceptions to this. Maybe very rarely, this is how many bonds they're going to make. Okay, so here's an example with carbon. We saw that carbon will make 4 bonds. It has 4 valence electrons, so it's going to share and make 4 bonds while it's sharing. So here's what it's going to look like when it's sharing those electrons, and it's going to have those 4 shared bonds there. We can draw these in different ways. We can use the electron dot to show the valence electrons bonding, or we can show the Lewis structure. And then this is a space-filled model. So those are different ways that we can model these. Let's see if you can draw this one. Draw the Lewis structure for phosphorus trichloride, PCl3, which is used in pesticides and flame retardants. So see if you can draw that one. Okay, so first what you do is you'll put your P in the middle. Whatever there's the least of is probably your central atom, and since there's only one of them, and then the C's are going to be coming out from there. Then you look at how many total electrons you have. So here the P is going to have 5 outer electrons, and the chlorine is each going to have 7, but you have 3 of them. So you have 21 total electrons there to bond. If you add those together, you've got 26 outer electrons to work with, and we're going to distribute them evenly all over this molecule. So first, we're just going to try to bond these 3 together. Remember that each bond is 2 electrons, so we have used 6 electrons out of the 26. So there we are. We have our 6 electrons used, and let's try to place the remaining 20. We have 20 left. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, and then we can put the last 2 here on the phosphorus. So that's how we can arrange the rest of them. These are all lone pairs of electrons, and then we have 3 bonding pairs. We can also make double and triple bonds with Lewis structures. A double bond is when it's sharing 2 pairs of electrons or 4 electrons. So here you can see in this CO2, carbon dioxide, it's sharing 4, so that's going to make a double bond, and this one's sharing 4, so that's going to make a double bond, and then you're going to have 2 lone pairs on the outside. Here we have cyanide, and you can see that we're sharing 3 pairs or 6 electrons. That's going to make a triple bond, and then we have a single bond here. And all of these are going to form octets. So your nitrogen is going to have 8, your carbon is going to have 8, and then your hydrogen is going to have 2. There are exceptions to the octet rule, so they don't always obey the octet rule, of course, because it's nature. Some of the example ones are hydrogen. So hydrogen just needs 2 electrons, so that's a weird one. It's not going to need 8. And then these nonmetals often have weird numbers, and they don't obey the octet rule. So phosphorus, sulfur, chlorine, bromine, and iodine, they can form like extended octets, and then sulfur is another one. SF6 can form 12. And boron can do fewer than 8 electrons. All right, now we're looking at section 6.7, which is electronegativity and bond polarity. So these are characteristics of atoms that help us predict what kind of bond they're going to make. This is a table that has these little values on it. These are electronegativity values. And we can see in this table, if you follow this trend, we go from 1 to 0.9 all the way down to 0.7. So these electronegativity values go down, they decrease this way, and then you can see that they increase this way. So there's your label. Fluorine has the very highest electronegativity on the whole table, and cesium has the very lowest. And we ignore the ones in the middle. So electronegativity is the atom's ability to attract electrons to make a bond. So it's how good it is at getting electrons and sharing electrons. And you can see the trend that we saw in the last slide. Fluorine is the highest, and then metals are usually low. Cesium is the lowest. So here's that trend again. And this electronegativity is going to determine if the bonds are polar or not. So polarity is the ability of an atom, or sorry, a molecule to share the electrons evenly or not. If a molecule is sharing evenly, so you can see here that these electrons are being shared evenly, this is a non-polar bond. So shared evenly is nonpolar. Shared unevenly is a polar covalent bond. They're both covalent because they're both sharing, but notice here that this chlorine is hogging the electrons. It's got most of them over there surrounding it, and the hydrogen is just sharing too. That's all it wants, but this just happens to be a polar bond because it's sharing unevenly. And you can see these little symbols here. These are called dipole moments. So this is going to be the positive side, it has fewer electrons, and this is going to be the negative side, it has more electrons. Okay, so nonpolar covalent bonds have to be between nonmetals because it's covalent, and this is where we have equal sharing, or almost equal. It's not always perfect. So here it has to be within this range of 0 to 0.4. Here are 3 examples where they're not exactly even in the polarity and the electronegativity, but they're pretty close. So what we do is we take their electronegativity values from that figure where it have the numbers on it, and we just subtract them. And we look at what that difference is. If that difference is from 0 to 0.4, then they are nonpolar covalent. If the differences are between 0.5 and 1.8, and different textbooks will have different cutoffs for these. So I've seen it as high as 2.1. Those are considered polar covalent. Remember, they have to be between nonmetals, but this is an unequal sharing of electrons. So that's the difference in electronegativity. They have these dipole moments. So these are the dipoles. And we're using the plus to show where there are fewer electrons and the minus to show where there are more electrons. And then we also use this arrow that points to the negative end of the molecule. So you can see it's pointing to the negative end here, and then you put a little plus here on the positive end. And this is a Greek letter delta. Ionic bonds, you can also use electronegativity for. They have a really big electronegativity difference of 1.8. So you take those numbers, you subtract them, so you have your metal and your nonmetal. That is a 2.2, and so that's definitely ionic. And these are always between metals and nonmetals. So if you're not sure, you could subtract electronegativity. If it's greater than 1.8, then it's ionic. So here's a slide that shows that all together. If it's 0 to 0.4, it's nonpolar covalent. If it's 0.5 to 1.8, it's polar covalent. And if it's 1.8, it's ionic. This is kind of a squishy rule, so between 1.8 and 2, it kind of varies. So you might see different books with different cutoffs. Here's another way to visualize that. If the difference is 0 to 0.4, you can see they're pretty evenly shared, nonpolar covalent. If it's 0.5 to 1.8, pretty big difference. It's pulling over this side more, is more negative. It's hogging the electrons. That's a polar covalent. And then if it's really hogging the electrons, give and take, then it's ionic. And here are some examples of some common ones. And you can see the electronegativity differences and then what type of bond they have. Okay, so see if you can identify these based on their electronegativity difference as nonpolar covalent, polar covalent, or ionic. And you can also use clues about whether it's a metal and nonmetal or two nonmetals. Okay, there are your answers with the differences and the type of bond. Okay, 6.8 is where we are trying to determine the shape and polarity of molecules. So when we look at molecules like this in 2 dimensions flat on a piece of paper or a screen, that's not really what they look like. They actually exist in 3-dimensional space. So this is one way that we can draw it, and this is another way. This shape here is known as a tetrahedral, and this is another way that we also draw it. This solid triangle is showing that this H is coming out towards us, and then the dashed one is showing that the H is going behind the screen. So this is the wedge dash notation. So we're going to try to predict what the 3-dimensional models would actually look like. We use this theory called VESPER. It's the valence shell electron pair repulsion theory to try to predict what these molecules are going to look like in 3 dimensions. And this is based on the electrons repelling each other. So the electrons are trying to get away from each other in 3-dimensional space because they're negative, so they repel. And this helps us to try to figure out what the shape's going to look like in 3 dimensions. So here is an example. This is carbon dioxide. We've already learned how to draw this guy. And since these electrons are going to try to repel each other, these lone pairs on the oxygens, this shape is going to be linear. These are going to be straight across with the carbon in the middle. So that's what carbon dioxide will look like, and we call that shape linear. And then if we have a shape like this, H2CO3, this is formaldehyde, it's going to have the carbon in the middle, it's going to have the oxygen bonded to it, double bonded, and then H is coming off each side. So we might think it looks like this, but it's actually going to look like this because they're all going to try to get away from each other. And it is, if you look in 3 dimensions, it is going to be flat on a piece of paper, because if this one moved over into this region of space, it would be too close to these. So this is where they have to be as far away as possible from each other. And this shape is called trigonal planar. This angle is 120 degrees, which you would expect because a circle is 360. We can also have a situation where an atom is only bonded to 2 things, but it still has a trigonal planar shape. So let's look at why this is. In this molecule SO2, you're going to have a single bonded O, which is here, a double bonded O, which is here, and then a lone pair of electrons, which is here. So it's not actually going to have this shape because this lone pair of electrons is going to be pushing those other electrons down. It kind of seems like it would have a trigonal planar shape, but actually this lone pair up here is really good at pushing those down, so we actually call this a bent shape. So this lone pair here is kind of imaginary, like it doesn't exist. One of your labs, I'm not sure how, I don't remember how well it aligns to this particular chapter, but you'll be modeling these with your kit, and you'll use like these little balloon things to represent the lone pairs. Like, they're not balloons, they're like, sometimes we use balloons, but they're like little teardrops. I think mine are pink or orange. So that's modeling the lone pairs, showing it pushing down. So those models that you have in your kit are to demonstrate VSEPR. CH4 is the tetrahedral one. So you would look at it on a piece of paper like this, but that's not how it's actually going to be because these H's are going to want to get away from each other. And so the shape is tetrahedral. This angle is 109 degrees. NH3 is another cool one. This is one we haven't seen yet. So this is what we think it might look like, but in reality, the lone pairs are going to push down the H's to kind of minimize their interaction with each other. And it actually makes this sort of tetrahedral shape, but it's actually the lone pair is going to push down a little bit harder than normal tetrahedral. So this shape is actually trigonal pyramidal. That's the name of the shape. If you have 3 bonds on a lone pair, it makes a trigonal pyramidal shape. And then H2O is another shape. H2O has the O in the middle with the 2 H's, and then you have 2 lone pairs of electrons there. And remember, these are kind of imaginary. You can't really see them, but they're going to be pushing down those 2 H's more than normal because these lone pairs are pretty repulsive. So this is going to be a bent shape. So you can see there that it's pushed down a little bit more than it would be if it was like a tetrahedral shape. Okay, so here are a chart summarizing this. So you have all your shapes here, your linear, trigonal planar again, tetrahedral all the way down. This is if you include the electrons, but if you don't include the electrons, the lone pairs, then this is the molecular shape. So you can see that there's 2 different types of shapes. This is if you include those lone pairs, and this is if you don't include them. So make sure that you understand these interactions well. Let's see if you can do this. Let's predict the shape of H2S. First, you'll draw just a simple Lewis structure. You've got two lone pairs and then two bonds here. And then let's see if that's what the shape actually looks like when we consider VSEPR. So with VSEPR, we can see that these lone pairs are actually going to push down the H's. And so this shape here is going to be bent. It's just the same shape as water. And this angle is 109. In real life, it's actually probably closer to 104.5 because those lone pairs are pushing it down. But we just simplify and call it 109. It is less than 109 though. See if you can determine the number of electron groups, the lone pairs, and use VSEPR to determine the shape of these three. Okay, so there you are. Those are the Lewis structures. And then this is how you would arrange them to minimize repulsion in the VSEPR model. And these are their shapes. Okay, now we're going to look at polarity of molecules. So remember, nonpolar means that they're sharing equally, but sometimes just because a bond is polar, it doesn't mean that the whole molecule is polar or nonpolar. In other words, you can have a molecule with polar bonds, but the whole thing can be nonpolar. So it says here, polar bond, there can be polar bonds. What does it say? With polar bonds can be nonpolar if the polar bonds cancel each other. Yeah, that's what I'm saying. So if we look here, the bond between C and O is actually polar, and this bond is also polar, but overall it cancels it out. So this whole molecule is nonpolar. Same thing happens with CCl4 here. You do have 4 polar bonds, but they all are pulling in opposite directions. So overall this guy is nonpolar. So I'll say it again. You can have polar bonds in a nonpolar molecule. And then these are polar molecules. So HCl has a dipole. It's not canceled. So this is definitely a polar bond and a polar molecule. Polar covalent, right? Here's another one. This is water. So you can see here that the arrows are pointing towards the negatively charged oxygen. It has this bent shape, less than 109 degrees. And so you can see here that overall this is polar. It's really, really important to know that water is polar. That's a really important characteristic of water, and it makes all life possible. It's really important in medicine and health. So water is a polar molecule. Remember that nugget. And here's another polar molecule. So you've got 3 polar bonds, and based on this shape, it is going to be polar. If we didn't know the 3-dimensional shape, we wouldn't know whether it was polar or not. That's why it's important to know what the VSEPR is actually going to look like. And remember, the shape is trigonal-pyramidal. Okay, so we can determine polarity using electronegativity. So again, we can look at these bonds to determine if this guy overall is polar or nonpolar. We subtract these and find a difference of 0.5. And since it's over 0.4, it's going to make it polar, covalent. And here we see that this is what the structure is going to look like. And we have 2 polar bonds facing this way. So overall, this is a polar molecule. They're not canceling. See if you can identify overall these 3 molecules if each one is polar or nonpolar based on the steps we just used. Okay, so here you are. There's the differences in the charges. That means there's a difference of 0.7. So it's polar. This one's also 0.7 and this one's 0.4. So this one's nonpolar. And then we have to sketch them and look at them in 3 dimensions. And we can see polar, polar, and nonpolar. All right, last bit here is on 6.9, intermolecular forces and compounds. So when we have polar or nonpolar molecules, the molecule is also going to interact with other molecules. You can see here this is a water molecule, which is polar, and another water molecule. And the positive part of this guy is actually going to interact with the negative part of this water. And so they're going to form hydrogen bonds between molecules. That's what we mean by intermolecular forces. So here's some cool examples. When we have covalent molecules, they're going to interact with each other. They're going to have intermolecular forces called dipole-dipole attractions. And we see this most often with fluoride, oxygen, and nitrogen. Hydrogen's going to bond with them. Here is an example with HCl and HCl. So we have the negative and the positive bonding that's going to form a dipole-dipole attraction. It's not a very strong bond, but it's an important bond. And this is NH3 and NH3 bonding. This is super important in living things. Polarity is probably one of the reasons why living things exist. It's definitely one of the reasons. So we're forming really weak hydrogen bonds here, but they're super common, super important. We can also have dispersion forces that happen with nonpolar molecules. So nonpolar molecules also bond and interact with each other, but not as well as polar because they don't have that positive and negative, but they can form these temporary dipoles when they're near each other. So you can see that they kind of make things a little bit charged and make it a little bit asymmetrical, but they're still nonpolar. So here they have like temporary dipoles where things are kind of shifting and dispersing. Wow, I'm tired. Dispersing, but they're still overall nonpolar, and they're weak bonds. These intermolecular forces affect melting point because these molecules are bonding with each other, and they're affecting whether, like, those bonds have to break in order for something to melt, to go from a solid to a liquid. So related to the strength of the intermolecular forces, and you have a higher melting point if there's stronger forces. Ionic bonds have the strongest melting, or the highest melting points, because those intermolecular forces are really strong between ions, between the positive and negative. So here are some melting points of some different common substances. You can see ionic bonds here are super high. The ones that have hydrogen bonds are higher, and then dipole are getting lower, and then the ones that have dispersion forces that are nonpolar are even lower. And then here is what this looks like as you're looking at it. So you can see ionic bonds here and covalent bonds and the difference there, and what those intermolecular forces are going to look like. And then you have between molecules, so you have polar molecules here. These are dipole-dipole interactions between ionic bonds. Nope, just kidding, not ionic bonds. These are both nonmetals. And then these are dispersion factors in nonpolar molecules. Okay, so see if you can identify the main type of intermolecular forces that you'll see here. Are you going to see ionic bonds, dipole-dipole, hydrogen, or dispersion forces with these 5? And there are your answers. All right, thanks for hanging with me through this one. And here's a nice concept map of everything we went over in this very dense chapter. So good job learning chemistry. See you next time.